Hi, you found this screencast because you might need some help with writing electron configurations. Electron configurations in first-year chemistry and in advanced placement chemistry are ways in which we look at how electrons are arranged around a nucleus. It also tells us, with the help of some higher-level mathematics, where statistically we can find a high probability of locating the electrons around a nucleus of an element. So let's take a look at how this works. One of the fundamental principles for how to write an electron configuration is understanding how the orbitals or the sublevels are arranged using quantum numbers. So when you're looking at something like this, which is called an Aufbau diagram, which translated means filling up, we're going to take a look at how you actually go through and put electrons into this. The lowest level of energy for an electron configuration is the 1s energy level. Now you'll see that there's a box located in multiple different spots on this chart. As a matter of fact, when we're talking about the p sublevel, there's 3 boxes. With the s's, there's a single box, and with the d's, there's 5 boxes. As a matter of fact, this is the number of orbitals for each shape. So in the d sublevel, there are in fact 5 different orbitals. With the s sublevel, there's 1, and with the p's, there's 3. There's one shape sublevel that's not included on this diagram, and that's the f sublevel. That includes 7 different shaped orbitals, so we'd have 7 boxes. Now within each of these boxes, you can fit, within each box, you can fit 2 electrons. And those 2 electrons have opposite spins. If we're using boxes, normally we'd start here at the very bottom, which can contain a maximum of 2 electrons since there's only one box. So we use arrows, called an orbital diagram, to represent this. When there's 2 arrows in a box, that orbital is said to be full. So on the 2s orbital, which is the next one in order, we can fit 2 electrons. Now, in the 2p orbitals, there's 3 boxes. An interesting thing about electrons is that when you're filling orbitals of the same energy level, they go with parallel spin first. So let's say, for example, we had to place 2 electrons in the 2p orbital. Those 2 electrons would have parallel spins, so if one of them has an up arrow, the second one also has an up arrow, but it's located in the second box. So we take turns here putting the electrons in the different boxes. The third electron in the 2p orbital goes in the third box. The 4th electron goes in the first box, but with an opposite spin. That's called the Pauli exclusion principle, so that the 2 electrons have opposite spins. The fact that the electrons go in parallel directions first, that's called Hund's rule. So between the Aufbau principle, the Pauli exclusion principle, and Hund's rule, we have the basic idea for how to write an electron configuration. So the 3 rules put together is that the orbitals fill in order from lowest to highest energy, that electrons have to have opposite spins to occupy the same orbital, and that electrons will fill orbitals of the same energy level with parallel spin before pairing up. Now, if the Aufbau principle is a little, or the Aufbau diagram is a little confusing to you, we can also use a periodic table to help us with this. You'll notice that this periodic table in this diagram is arranged a little differently than most charts in our room. The F block orbitals are actually inserted where they're supposed to go according to atomic number. If we number the rows on the periodic table 1 to 7 off on the left-hand side of our screen here, and on the right-hand side they'd be 2 through 7 because the first row doesn't have anything in the P block, then we can start to see kind of this order. So the boron would be, the element boron would be in the 2nd row, aluminum 3rd row, 4th row, 5th row, 6th row, and 7th row. Now, a couple of interesting things here is that the d block orbital is available in the 3rd energy level, but we don't see it till we hit the 4th row of the periodic table. So the d row actually starts with 3, 4, 5, and 6. Another interesting thing is about the F block of elements. We can have them in the 4th energy level, but we don't see them till the 6th row. So this would be 4 and 5 for the Fs. Now, the way the periodic table is read for given an electron configuration is we read from left to right, top to bottom, until one of 3 things happens. So when writing electron configurations, basically we count elements until 1, you find the element in question, 2, you find the end of a row on the periodic table, or 3, you find the end of, in this case with this periodic table, we'll call it a block. So we find the end of a block, whether that be S, P, D, or F. So when we hit the end of one of those blocks, we also stop counting electron configurations. So when we take a look at how to do this, it becomes very important that we have a periodic table available to help us do this. Let's try to write a couple electron configurations using this. So we're going to refer to this periodic table. Those of you at Arapahoe High School, you have a long periodic table that we constructed in class one day. It should be on legal size paper. So if you don't have that out, hit pause right now and go find that periodic table so we can work on these together. Here we go. There's 4 elements on the screen, and we're going to write the full electron configurations for these. So for hydrogen, this is the simplest electron configuration, and it's the one that we always start with. The element hydrogen is located in the upper left corner of the periodic table. It's in the first row of the periodic table, and it's in the S block. And you should have your periodic table labeled with row numbers and shapes S, P, D, and F. Now, if you count the number of boxes until you find hydrogen, you'll find that hydrogen is the first box. We represent that with a superscript 1. What this information tells us is that hydrogen's only electron is in the first energy level. We can find it located in an S-shaped orbital, and there's only 1 electron. That's what that information tells us. So let's try silicon. Silicon is in the second row, P block. However, with electron configurations, we always start in the same spot. So we start in the first row, S block. So count with me the elements on the periodic table. Hydrogen, helium. That's 2 elements, and that's the end of the first row. So we write a superscript 2. We are now on the second row of the periodic table, S block, and we've got lithium, beryllium. That's the end of a block on the periodic table. So we write a superscript 2. Now we're still in the second row of the periodic table, working left to right, but we are in the P-shaped orbitals: boron, carbon, nitrogen, oxygen, fluorine, and neon. That's 6 boxes. That brings us to the end of the second row on the periodic table, so we write a superscript 6. We're not to silicon yet, so we write the row of the periodic table we're on now, the third row, third energy level, S-shaped block, sodium and magnesium, superscript 2. Still in the third row of the periodic table, but now the P-shaped block, aluminum and silicon. That's the element that we're interested in. We only counted 2 boxes in the third row, P-shaped orbital, so we write a superscript 2. That's the electron configuration for silicon. So that gives the arrangement of all the electrons in an atom of silicon and where we have a high statistical probability of finding them. Bromine. Let's try bromine. Bromine, we'd start with hydrogen, 1s, hydrogen, helium, that's 2. Second row, S block, lithium, beryllium, that's 2. second row P block, boron, carbon, nitrogen, oxygen, fluorine, and neon, that's 6. Third row S block, sodium and magnesium. Third row P block, aluminum, silicon, phosphorus, sulfur, chlorine, and argon, that's 6. Fourth row S block, potassium and calcium. Now we're to the transition metals, and if you remember what we did on the periodic table, when we hit the D blocks, it is 1 energy level behind. So since the S orbital was in the 4th energy level, the D's will be in the 3rd energy level. So we've got 3D, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc for a total of 10. And then we're back to the 4s, 4th row, P block, gallium, germanium, arsenic, selenium, and bromine. 5. There's the electron configuration for an atom of bromine. Element astatine, element number 85, is something I'd like you to try on your own if you haven't already. So hit pause on this, and when you hit play again, you'll see the electron configuration for astatine. Welcome back. You should have a electron configuration that looks something like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, and 6p5. That should be the electron configuration that you have written for element number 85. Now what you see here is you see the example of the longer the electron configuration, the more difficult it becomes. So there's actually a shortcut method that we use for writing electron configurations. It's called the abbreviated electron configuration, also called a noble gas shortcut. And we're going to look at 3 elements: phosphorus, francium, and argon. And what you actually do when you're working on these is you skip backwards to a previous noble gas. So this shows the core as a noble gas and then valence electrons outside of that. So what we get here for phosphorus, if we find phosphorus on the periodic table, the noble gas, which is the element in the furthest right column of the periodic table that precedes it, is the element neon. So we write neon in either brackets or parentheses. So we get neon in brackets, and that basically tells anybody that's looking at this that instead of starting with hydrogen as usual, we're starting with the element after neon. So we've got neon, which then puts us in the 3rd row of the periodic table, S block, with sodium. So we just start, instead of with hydrogen, we start with sodium. So we get 3s2, 3p to get to phosphorus 3. So for francium, it works really nice. Francium is element number 87, bottom left corner of the periodic table, and the noble gas on the far right side that precedes francium is radon. So we write Rn and put it in brackets. So that represents the core electrons, or the kernel, and we're going to then show the outermost, or the valence electrons, which in this case just happens to be 7th row, S block, and francium is the first element listed. So that's the noble gas shortcut. So for argon, which is element 18, which is a noble gas, we work it the same way. We skip backwards to the previous noble gas, which would be neon, is the previous noble gas, and then the outermost energy level would start with the 3rd row, S block 2, which is sodium and magnesium, and then 3p6 to get to argon. So it shortens the electron configuration significantly. I hope this helps with writing electron configurations. And